All right, I apologize. That video went longer than 15 minutes. This is going to be part 2 of finishing up this kinetics analysis. I will pick up here right where I left off. So we had copied the top graph to make this second graph, and I had switched the data that was being plotted. And so now what I want to do is change the labels on this second graph, because this is no longer the 0th order kinetics graph. This is now the 1st order kinetics graph, because what we are plotting here is actually these natural log of the concentration values that we have in the D column here, right? So that corresponds to the 1st order kinetics graph. So that also means that for this graph, we would be determining that the exponent on the reactant would be equal to 1 in this case, if this one's the most linear of all 3 of the graphs that we're creating. Because we're plotting natural log of the concentration for the Y values, I want to also change this over here to natural log of the concentration. And you are welcome to change this to natural log of C if you want to. And then the units on natural log of C are kind of weird, so it's totally fine if you just want to leave that as natural log of C there. Okay, so what I was trying to show here is sort of this shortcut of how if you get one of your graphs finalized, it makes it a lot easier to then make small adjustments to the other graphs you have to make, so that you don't have to do the formatting every time for each one of these graphs. I am going to go ahead now and make the 3rd graph. And to do that, I'm going to copy again the 2nd graph that I just created, and I'm going to paste this below. I'll move this down so we can see it below here. And for this, I might also zoom out a little bit here so we can try to see all 3 of these graphs at the same time. Yeah, that makes it a little better there. Okay, so for this 3rd graph, I'm going to double click on it again. I'm going to come over here to the the setup tab under the chart editor. And again, I just basically want to change the Y values that are being graphed in this situation. So right now it's the natural log of the concentration, but really I want this to be this 1 over the concentration column for this 3rd graph. So that is my E column in my spreadsheet. So again, all I have to do is change the D's that are being plotted here to E's in the data range, and then click OK. Now, if for some reason you don't feel comfortable editing these, I'll just point out that you can also just select this range, right? So when you have that window open where it says select a data range, you can also just select it in the spreadsheet if that's easier for you. Okay. So I clicked OK. Now you'll notice my graph looks a little weird, but that's again because of the fact that we had set the vertical axis to have a max value of -11 on the previous graph. So I want to go in and just fix that now and change it so that there's not a max value set. And you'll notice now the data is showing up nicely on this graph for my 3rd graph for this kinetics analysis. So I got to change my labels again, because this 3rd graph is now the 2nd order kinetics graph. And so if this one's the most linear, we would be getting an exponent of 2 for this reactant. I also want to change my Y values over here, because again, this is not natural log of concentration anymore. It's now 1 divided by the concentration. And again, it's fine if you want to leave that as 1 over C. It is often the case that you'll show all 3 of these graphs at the same time. So notice that on the 1st graph, if we're setting the y-axis as concentration, it's understood that ln of C means natural log of the concentration for the 2nd graph, and 1 over C means 1 over the concentration for the 3rd graph. So you don't necessarily need to put in units on those or try to write out that concentration term again. Okay, so all 3 of these graphs are now finalized for trial 1. I'm going to note, just for the sake of the concepts in this lab, that the 2nd graph for my data that I have here is showing up as the most linear. And we can tell that just from the way that it looks, right? You can see that the trend line fits that data pretty nicely. But we can also see that based off these differences in the R² values. Let me zoom back in so that's a little bit easier to see. Right? So notice the 1st graph had an R² of 0.855, so that's not very good because it's not close to 1. The 2nd graph for 1st order kinetics has a R² of 0.996, so that's great. That means it's pretty close to 1. And when we compare that to the third graph, which is somewhat close to 1, but it's not as close to 1 as the second graph, right? So 0.937 is less than 0.996. So that means my first order kinetics graph here is the one that tells me that this reactant is first order. Okay, so I'm going to go ahead, just to point this out to myself, I'm going to change the colors excuse me, on this graph. I'm going to just go ahead and make the data red, because that'll make it stand out to me that, hey, this is the graph that is showing me that this is a first order dependence. Now, the other thing that's special about this graph is the slope of this graph is going to give you the rate constant. So up here in the equation for the line of that trend line, I can take this value, this negative 3.02 times 10 to the negative third, and I can use that to determine the rate constant. Now, because this slope is negative, remember that for these kinetics graphs, any of the slopes that are negative, the slope is going to be equal to negative the rate constant. So basically what that means is for this graph, I know that the rate constant is actually positive 3.02 times 10 to the negative third. And that would be a rate constant that is also in units of molarity, since we plotted all of our data, right? We calculated these concentrations over here in the C column in molarity, right? And again, that's coming from the fact that our absorption coefficient that we had back here was in molarity, right? So don't forget to include units on your rate constant, and those units are definitely going to have molarity in them. Okay, so at this point, we have covered basically all of the analysis for trial 1. We need to do the exact same thing for trial 2. So let me show you another shortcut to make your life a little bit easier here. Because I've got everything done for trial 1 in this sheet, I'm going to go ahead and duplicate this sheet and then call this next one trial 2. Now, everything looks exactly the same right now. If I switch back and forth, right, you can't tell any difference here between these two sheets. But I'm going to change that because I'm going to go back to my raw data sheet where I had my trial 2 values. And I'm going to note here the times are the same, so I don't need to copy those over. But I do want to grab these concentration values that I have for trial 2. So I'm going to copy those values. I'm going to come back in here to the trial 2 page. And actually, let me copy both the absorbance and the concentration values, since I forgot that I had those on that sheet. So let me just copy both of these. Okay, so I'll do the absorbance and the concentration values for trial 2. So I'm going to come back over here now, and in this cell, I'm going to come up here to Edit Paste Special, and I want to make sure I choose values only, because if you remember, some of those cells from that other page were programmed as equations, and so I just want to put in the values here. So I pasted in the values for trial 2, and what you'll notice is because our equations that we have programmed in here are pulling from this C column, all of those values updated, and since our graphs are all pulling from the data in this sheet, all of our graphs updated. Now, if you don't believe me, I'll switch back and forth here between these two. So pay attention here to the values we have for these two columns. When I switch to trial 1, notice that they're different, right? Also, pay attention to the two graphs here. When I switch back to trial 2, they're a little different, right? So note, I just did all of the analysis for trial 2 in like the blink of an eye, right? Because all I had to do with having this sheet nice and set up and programmed and ready to go, all I had to do was paste in the new concentration values, and it basically spit out everything for me. Now let me zoom back out again here just so I can show you guys the 3 graphs. Okay, let's go back to trial 1. So here were the trial 1 graphs. Again, we can see that the second graph is the most linear. And in trial 2, we're still expecting to see the same reaction order for the crystal violet, because the thing that changed between trial 1 and trial 2 is the sodium hydroxide. So we did already do the analysis for the sodium hydroxide in a different way to figure out what the reaction order was for the sodium hydroxide. This particular method we're using here really is focusing on just the crystal violet. So by doing trial 1 and trial 2, yes, that the purpose of doing it twice was to figure out sodium hydroxide's reaction order. But what's nice about this is we should expect to see the same reaction order for the crystal violet in both of these trials. And so that allows us now to average the rate constant that we're going to get, and also just check to see that both trials actually gave the same result, because that's just kind of further proof that you have some confidence in this reaction order that you're going to assign to the crystal violet. So again, here's trial 1. Again, that second graph was highlighted because it was the most linear. It had the R squared value that was closest to 1. And if I switch over to trial 2, you'll notice same result, right? That second graph is the most linear. It may be a little hard to see here, but let me go ahead and zoom back in and point out that the R squared value for the first graph is 0.944, but for the second graph it's 0.998, and for the third graph it's 0.972. So again, that second graph, which corresponds to first order, is the most linear and therefore gives me the reaction order. Now you'll notice that the value I get for the slope here, let me zoom back in. The value I get for the slope in trial 2 is negative 1.84 times 10 to the negative third, but in trial 1 it was negative 3.02 times 10 to the negative third. So the rate constants between these two graphs are slightly different, but at least they're on the same order of magnitude, right? They're both 10 to the negative third. So I would want to report both of these values and then take the average of the values to get what my average rate constant is between the two trials, right? And so again, that just demonstrates that by doing the reaction twice, we actually get slightly more accurate data because we're able to average out in case there's any experimental errors occurring in the data. All right. That pretty much wraps this up. Remember that for the formal writing, you want to be including all 6 of these graphs. One final change I would make to your titles is to make sure they are labeled with which trial they are. So this is trial 1 for these 3 graphs that I had on the trial 1 page. So I'm going to go ahead and label these as trial 1. And then I'm going to switch over to my trial 2 and I'm going to label these second set of graphs as trial 2. That's really important because otherwise somebody looking at all of these graphs is not going to understand why you have sort of multiple of the same type of graph, right? So it's a good idea to include trial 2 on here for all of these. For those of you that may be wondering why we don't just combine trial 1 and trial 2 in the same graph so that we could just have 3 graphs with the trial 1 and trial 2 data plotted, like for example, plotting both trials on this first graph. The reason for that is because if the data overlaps pretty significantly, it might be kind of hard to see the differences between them. But you are welcome to fiddle around with that. If your data is different enough between the 2 trials, you can try plotting them on the same graph and see if it's easy to interpret. The only other suggestion I would probably make if you do that is to make the 2 trials a different color so that it's really clear which trial is which one in the data set. So again, if you want to fiddle around with that, you're welcome to do that. Just make sure that the 2 sets of data are clearly able to be interpreted and that they're not overlapping too much. All right, I think that pretty much wraps up this analysis. If you have any questions, please feel free to either post in the comments on YouTube here if you want to, or you can reach out over Campus Wire. But I hope this was helpful. I hope it's easy to kind of follow along. Just let me know if you need any help. And also, due dates for things here are pretty lax on this experiment. I know this one is pretty involved. So if you need some extra time, just reach out and I'm more than happy to give you a few more days to finish things up. All right, good luck.